Yeah, so my first slide is actually quite similar to Rudy's slide, just there's a small number 2 at the end of the title. So this will really be the second part of the tool. So Rudy gave a lot of history of the problem and gave some of our weaker bounds. Actually, a lot of the elements that Rudy mentioned, I will use again in these slides. So in particular, the Johnson graph that he introduced and the cover, the idea of using a cover will play a central role in what I'm about to tell you. So just to kick it off, I copied some of the bounds from Rudy's slide. So there's Piff's upper bound, there's the Graham and Sloan lower bound, using the construction in the Johnson graph. Now I want to talk about these two theorems. So the first one says that we can improve this extra log n factor to a factor 2. So basically what it says is that our upper bound is within a factor 2 of the lower bound due to Graham and Sloan. And the second result shows that it's actually false as it states here, or at least we didn't prove it. We proved that the logarithm of the number of factors
That's what I was
asymptotic to
wondering. I knew the one number wrong, but this was a big deal.
Yeah, so it's the logarithm of the number of matroids is asymptotic to the logarithm of the number of sparse paving matroids. So we have an upper and a lower bound on the number of sparse paving matroids on the number of matroids, and know that the two are asymptotic in this logarithmic setting.
So that second theorem with the addition of the logs follows immediately from the first theorem, right?
No, I don't think it does, because this one says that there's a factor 1 in front.
Yeah.
This one says that there's a factor 2 in front, so they do not.
Yeah,
quite
right.
compare. But it's only this factor 2 difference.
Right.
So we know that this result, including the logs, holds, but we don't know which one of the two bounds is closer to the actual bound. All right. So my talk will actually be in 3 parts. First, I will focus on the sparse paving matroids using this Johnson graph idea that we saw before. So that's part 1. Then I will try to extend that to more general matroids, and that will give the first theorem on the previous slide. And then after that, I will prove the second theorem. So that will be part 3 of the talk. So yeah, let's first try to count the stable sets in regular graphs. So Rudy already mentioned that the Johnson graph is a regular graph. The result that we get works for general regular graphs, and then we apply it to the Johnson graph to find an upper bound on the number of sparse paving matroids. So that's basically what the first slide says. So our main theorem in this part is, if you have a graph on capital N vertices that is deregular and has minimum eigenvalue of the adjacency matrix negative lambda, then we can put an upper bound on the number of stable sets in this graph. The upper bound is basically a binomial coefficient multiplied by a power of 2. Yeah, and there's some expressions for this alpha and sigma that appear in this bound. So this alpha is known as the Hoffman bound, which is an upper bound on the number of stable sets in a regular graph.
The cardinality of stables.
Yeah, the cardinality of a stable set. In a deregular graph with minimal eigenvalue, negative lambda. So that kind of explains why there's a power of 2, right? You have this largest stable set and you take all subsets.
If you know a better bound than the largest stable set for the graph that you're in, a better bound than the Hoffman bound, can you replace it in that statement?
Not necessarily. It might give some pointers as to how to improve our results. It's not automatically that it replaces the alpha in this.
Well, you can replace the 2 to the power alpha n by alpha n choose your better bound. in that theorem. Because this 2 to the power alpha n is counting all the subsets of a size alpha n that are stable. And if you don't know anything different about the size, you look at all subsets. But if you know that the biggest one is at size k, you will only be looking at all the guys of size most k. They are a subset of this alpha n set.
Yeah, that's right. Okay, so this is the main theorem that we prove in this part, and we want to apply it to the Johnson graph. And actually, all we are interested in is kind of the central Johnson graph, so where the number of elements in each vertex is equal to n over 2. Half. So this is related to what Rudy already told, that if you go to logarithmic scale, actually all you're interested in is the largest upper bound, and the rest doesn't really play a role. So if we plug it in and do some of the calculations, what we find is that the upper bound on the logarithm of the number of stable sets in this Johnson graph is basically 2 over n times the binomial coefficient. So 2 over n times the number of vertices in this Johnson. And there's some error term involved. And Rudy already mentioned that stable sets in the Johnson graph are precisely the sparse paving matroids. So that translates immediately to a bound on the number of sparse paving matroids. So this proves the first theorem from the introduction in the case of sparse paving matroids. Okay, so in the remainder of this part I will talk about the theorem and how to prove it. And it's a really nice technique actually. So I think it's originally due to Kleitman and Winston, somewhere from the 70s, I think. So the idea is quite cute. So what you want to do is you have 2 sets of vertices. The set A of available vertices that you can still choose in some kind of encoding, and the set S of selected vertices. The way you do it is, as long as there's many vertices available, then you take the one with maximum degree, you select it into your selected vertices, and as soon as you selected it, well, you only select it if it's stable, if it's in the stable set that you want to encode. So if you know that it's in the stable set, you know that all its neighbors are not in the stable set, so you can ignore them from then. So
I think so. It says encoding stable set I.
yeah.
That's sort of missed, so nobody can read that. But that's the object of this procedure.
Exactly.
Encoding a stable set called I.
So let's see how that works. You pick the one with highest degree. In this case, it's not in the stable set, so you just kick it out. You try again, you find another one that may not be in the stable set. You kick it out. Then you encounter a vertex that is in the stable set, so you select it, and that gives you all the information to decode kind of the neighborhood of this vertex. So you know that all the vertices in the neighborhood of this vertex will never be in your stable set. So you can kick out the whole neighborhood at once, and that's what makes this work. So you repeat this procedure until your set A is too small. And too small means less than the Hoffman bound. So in that case, we do not know whether it's worthwhile going further. So is this sort of clear? Okay, so here are some properties of the output of this procedure. So the procedure gives you a set S of selected vertices and the remaining vertices that you haven't looked at yet. And as soon as you select a vertex, if you put it in the set S, it has to be your stable set that you want to encode. So S is definitely a subset of the stable sets. And well, every vertex is either in S, in the neighborhood of S, or in A, but we've certified that in the neighborhood of S, there are no vertices in the stable set. So you also know that the stable set that you want to encode is a subset of S union A. So this kind of localizes where the stable set is in your graph. And this, I think, is the key point of the procedure. The set S that you obtain in this way actually shows you where to find the set A. Because you can run the procedure on the set S and it will output the same set A. Because all the choices that you make depend only on whether the vertex is in S. So the point that S determines A is very, very important. Because it shows that S serves as kind of a localizer to find the set A. So here's the analysis. So the first 2 points I already covered. There's the obvious bound on the cardinality of A, because you do not stop before it gets smaller than this. And I will show a bound on the number of vertices that you can select. So the point is that you have a small selector, S, that points you to the set A. And this means that the stable set that I've tried to encode is now encoded by S, and the remaining stable vertices that are in set A. So this is a small description of the stable set. And this gives the upper bound that we have. So the proof is here. The number of stable sets is now the number of selectors S times the number of possible subsets of stable sets that are in A. So A is kind of uncharted territory, so we don't know where the stable vertices in A may be. Maybe the whole set A. So in that case, that would be just 2 to the power cardinality of A. So that reflects in the structure of the bounded proof. Is this clear so far? So all that remains basically is to put an upper bound on the cardinality of the set S. If S can be too big, it's not very useful. But we can show that it's pretty small. Okay, so we want tight control over the degrees of the selected vertices. So we want to be able to say that if you select another vertex, you kill a lot of its neighbors. Right, so this is the main technical lemma that we will use for that. It was proved by Willem Hamers, and later I think by Noda Alon and Fan Chung. And it says that if you have a graph like we have, the regular minimum eigenvalue of the adjacency matrix, and we have a subset of the vertices, then we can put a lower bound on the number of edges that are spanned by the set of vertices. So we do not care too much about the exact form. What we care about mainly is 2 corollaries. So the first one is, if the set A contains more vertices than the Hoffman bound, then there has to be an edge. So this proves the Hoffman bound. And this is the corollary that we are interested in. It says that if the set A is larger than the Hoffman bound plus a constant factor of the vertices, then there has to be a vertex of a degree at least, this or that matter, depending on the constant. So this G of A is the subgraph induced by A. So this means that if you select a vertex from this set A, you put it into S, then it kills a lot of its neighbors that are still in this uncharted territory A. Our claim is that the set S is indeed at most sigma times the number of vertices. So sigma is this log d over d plus lambda. And it works as follows. So on the previous slide I proved if you are more than the Hoffman bound plus a constant fraction of the vertices, then you know something about the the minimum degree in this induced subgraph. So we chop up time into parts, and we say that the procedure is in phase J if you are, well, the Huffman bound plus something depending on J, and a little bit more. So the Huffman bound again is this lambda over d plus lambda. And the lemma on the corollary on the previous slide says that if you remove a vertex in phase J, so by remove I mean you take it from A, you put it into S, and you kill its neighbors, then this kills at least J neighbors in this induced subgraph, so that A becomes J plus one small vertex that you choose, and it's at least J neighbors. So that means that during phase J, which has length 1 over d plus lambda times n, you can add at most this many vertices to S. Because in every step that you add a vertex to S, you kill J plus one of its neighbors. And then you just sum up over all J, so J is from 1 to d, and that gives you the logarithm on top. So that proves the bound on S, and that concludes the proof of the first part. Everybody still happy? So then we move on to the second part. So in the first part we proved the bound on the number of sparse paving matroids by going to the Johnson graph. But there is a bit of a problem if you want to extend that to general matroids. So in part one we proved that stable sets in the Johnson graph, general matroids do not correspond to stable sets. So we have to be a bit smarter than that. So here's the procedure that we did in part one. Except that now we have the same output S and A, but for the vertices that are selected, we do not know anything about its neighbors. So they may be bases, they may be non-bases. And we have to certify in some way what are the bases and the non-bases in this neighborhood. So this is posing a problem at the moment. And that's all that's changed in this situation. This can be a real problem if S is very large and vertices are far apart, then the neighborhood is very large. So if you just want to sum up all the possibilities, then your bound becomes very, very weak. So here the covers that Rudy mentioned play a big role. So you want to certify in some way which neighbors of the set S are dependent and which are independent. So this is just the same definition that Rudy used in his slide. You're looking for flats and their rank. It acts as a witness for dependence. A witness means what? The inequality on top. And here's the lemma. If X is a non-basis, then we need at most two witnesses, two of these flats, to describe all the non-bases in the neighborhood of that set. And construction is quite simple. If the rank is very low, you can just take the closure of the set itself. And if the rank is R minus 1, then you want to add the closure of unique circuit containing X. So here's the kicker of this slide. We have the set S, and we need to describe all the non-bases in its neighborhood. So using this lemma, we need at most 2 times the cardinality of S of these flats, or flat rank pairs, to describe all the non-bases in this neighborhood. And this will solve all our problems. So this is basically one of the previous slides copied. We still want to describe the neighborhood of S, for which you use this combination of local covers. That gives the extra binomial coefficient in the theorem. So Rudy explains the 2 to the power n times n plus 1. It's basically a subset and its rank. It's a pretty weak upper bound, of course. But it's sufficient for our purpose. this puts a bound on the number of matroids of a given rank in a given browser. Okay, so there's the encoding on top. What we need now is not just S and the intersection of A with the non-bases, we also need this Z. There the theorem is again. And actually the binomial coefficient looks very nasty, but it's not really nasty. Because if you take the logarithm, still this bound on alpha is what dominates. So the new binomial coefficient disappears in this small O1. Then we use the kind of standard trick of summing over all the ranks to put a bound on the number of matrices. So really the bound that we find is dominated by this 2 to the alpha n. And that's maybe not so surprising, because what we do there is kind of really dumb. We just say, hey, this is uncharted territory. We just consider the possibility that all subsets in this uncharted territory are non-basic. So if in any way we want to improve this, say to match the lower bound by Graham and Sloan, so we get rid of this factor 2, we need to work on this set A. We need to do smarter stuff here. And that's what we're going to do in part 3. So any questions so far?
Can you go back to the definition of a witness, please?
Definition of what?
A witness. You had a slide.
Yeah.
Thanks. Good, that's good, thanks.
Okay. So as I mentioned, we want to do something smart about this set A. We do at the moment is really dumb. So let's try something new. And what we are going to do is basically find an independent set in this set A that will give us a lot of information. And what it gives is not an explicit upper or lower bound. It relates the number of matroids to the number of sparse paving matroids. So that proves the second theorem that I mentioned in the introduction, that the logarithm of the number of matroids is asymptotic to the logarithm of the number of sparse paving matroids. So let's start again on this slide. So this is the previous result that we have. The logarithm is at most 2 divided by n times the binomial coefficient, using the encoding SA and the combination of local covers C. What we're going to do now is, what we did was we tried to certify that if we select a vertex into S, then it kills a lot of its neighbors. And as soon as we reach the point of the Hoffman bound, we cannot be sure that it actually kills neighbors. So selecting vertices may not yield a lot. But it may still be the case that there are vertices of very high degree in this A. And it would still pay off if we could put them into S. It's just that we have no way of finding out how this will influence the size of A. So what we're going to do is first kick out every vertex of very high degree, in the sense that we encode them using S. And then we want to do something smart in the remaining set A. The smart thing is that we want to choose a stable set, a big stable set in the remaining. So that kind of looks like this. We choose this big stable set over there. And as soon as we do that, and we can show that this actually describes all the non-bases that we can still find in this A, then the result will follow. So the encoding is basically a big stable set, S, in the stable set that we find in A, plus a little more information. basically the covers that we used to describe the neighborhood of X. So here's the original procedure again. And nobody is to stop us to take it a bit further. As long as there is a vertex of high degree, we just take it, put it into S, remove its neighbors. So still the same inclusions hold. The bound on A we cannot improve because we do not have a result that we can apply. And S becomes a bit larger. So there's at most alpha times n vertices still in A. In each extra run of the procedure, we kill the minimum of R and n minus R plus 1 vertices. So this is the extra number of vertices that get added to that. And when we're done, we know that the maximum degree of the induced subgraph induced by A is very low. So less than R, less than n minus R. So this is a bit of a pain, of course. So generally we assume that R is less than half n. Okay. So now we still want to do something smart, right? We don't have a better bound on the size of A, so we still need to do something smart. And for that, we need to have a closer look at the neighborhood structure in the Johnson graph. So let's look at vertex X over there and look at its neighbors. So Rudy already mentioned that the number of neighbors is R times n minus R. And we kind of can organize them in this grid fashion. So if you look at the two indicated vertices on top, the one is obtained by kicking out X and adding Y. The other is obtained by kicking out X and adding Y prime. These two are neighbors of each other as well, because we can exchange Y and Y prime. So by removing this X, we can get a whole clique in this neighborhood. So these we call the rows indexed by X. And adding a fixed element Y will give you columns in the same way. So these are the columns indexed by Y. So there's R rows, and there's n minus R rows. And here's how we can describe the non-bases or the bases in the neighborhood of a vertex X. So if X happens to be a point set that has rank R minus 1, and it contains a unique circuit and avoids a unique co-circuit, and we can describe the neighborhood in this way. So we need to kick out some element of the circuit to destroy the dependence. We need to add something from the co-circuit in order to extend the hybrid plane in which it lives. That gives this kind of structure in the neighborhood, kind of a minor, you could call it, in the matrix sense. So you kick out a number of rows and columns, and what you're left with are the bases. So it's always this kind of block structure. And this will be the key point now for our encoding algorithm. So we've certified that this vertex X has very low degree, less than R, less than n minus R. So in particular, this means that there's always a row and always a column that are disjoint from the set A that we have.
So when a row being disjoint from A means that every set in that row is disjoint from A.
Exactly.
Right. Well,
yeah.
So a row is a collection of subsets, and every one of them is disjoint from A.
Yeah. Yeah, I like to think of them as vertices in the Johnson graph. So it means that all the vertices are outside this set A.
Right.
But when you're outside of A, you know whether you're a basis or a non-basis, right? You're either in S, then you're a non-basis, or you are a neighbor of S, in which case you can
So you
refer
have
from.
specification.
So for the row and the column that we have here, we know which elements are bases and which are non-bases. That will be very important. There's one way in which this can go wrong, and that is when this. Oops. Right. Let's go back. So there's one way that this can go wrong. That is all the elements in a row or in a column are dependent. Okay. So what it says there is that we want to make a technical assumption that the Matroid that we are trying to encode does not have loops and columns. And I think it was proved in your paper that this is true for almost all Matroids. So that doesn't really matter in our case. Now the point is, if you make this assumption on the Matroid and one of the rows and one of the columns is completely dependent, by which I mean all the vertices that are in this row and in this column are dependent, then the vertex X itself must be a non-basis. It must be dependent. Because if it would be independent, then you would either have a co-loop or a loop, depending on whether it's a row or not. So this means that we can actually restrict our attention to a subset of A, namely those vertices that have a row and a column that are disjoint from A, and both the row and the column should contain a basis, right? Because if that were not the case, then we would have an independent set. Then X would be independent, or you would have a loop or a code. So in this restricted set A prime, we choose a maximal stable set. So a maximal stable set means you cannot extend it to a larger stable set. In particular, that means that every element in T is either every element in A prime is either in T or it has a neighbor in T. And as T is chosen so as not to contain bases, we know that all elements in T are non-bases. So there's one case left, basically. So that's when you are in A prime and you are not in T. In that case, we do not yet know whether you are a basis or a non-basis. So let's see what we can do. So suppose that this X is an R set in which we are interested. We do not know whether it's a basis or a non-basis, but we know that it has a neighbor Y that is in T. And we can look at the neighborhood of Y, which looks like this. So it may have degree 2 in this set A, right? So there may be 2 vertices of which we still need to determine whether they are dependent or not. And we know that there is a row and a column that are disjoint from A, but we know that both of them contain a basis. But then we can use the idea of kind of projecting to this row and this column and using the block structure that we've seen before. So in particular, the vertex X, if you project down, it means a basis. For this guy, if you project to the right, it means a non-basis. So in particular, we know that X cannot be a basis. So it has to be a non-basis, and we have some more information. In the same fashion, if X would have been on the second row, it would meet a basis if you go down, it would meet a basis if you go to the right. So it has to be a basis. And this covers all the remaining vertices that are in the neighborhood of the maximum stable set that we choose, and the intersection with A prime. Okay, so let's wrap this up quickly. Our output is now SZ, set of available vertices A, and the maximum stable set that we chose. There's still inclusions, and it's easy to show that the union of S and T is a stable set. And then there's the technical lemma that basically covers the three different cases that we've seen. So if you have a matroid without loops and co-loops, then a vertex that is in A is dependent if and only if one of the following three holds. Either you have a row and a column that are dependent, or it is in T, or it has a neighbor such that you can do this kind of projection thing to the row and the column. And the matroid can be reconstructed from S union T, the big stable set, and we still need this local cover for the neighborhood of S. But it shows that the number of matroids is the number of stable sets in the Johnson graph multiplied by the number of possible covers. So yeah, as usual, that gives a multiplication, and if you go to the logarithm, then basically what it says is this sum of binomial coefficient vanishes. It's very small compared to the number of sparse paving matroids. So that gives the result. So is there any time left, Peter? Okay, great. So that wraps up kind of the technical part, the hard results that we've proved on matroid enumeration. Is it somewhat clear? Okay, great. Then we move on to the final part. Rudy already talked a bit about conjectures related to matroid enumeration, and I would like to talk some more about conjectures or open problems. So I have four nice open problems that we are interested in. And the first one is, okay, so we show that the logarithm of the number of sparse paving matroids is asymptotic to the logarithm of the number of matroids. But of course there's the much stronger conjecture that almost all matroids are sparse paving. And this is an old problem, as Rudy mentioned. So here's a quote by one of the papers that Henry wrote. And yeah, so it's kind of an old problem, and we don't quite know how to solve it. So the techniques that we use, or the bound that we find, it's kind of hard to improve it anymore, I think. So I find it likely that we need something much smarter than we're doing still. Okay, so related to that, here's what we show. We have the lower bound by Graham and Sloan. There's the upper bound from the first half of Matroid. And we know that the logarithms are asymptotic. And kind of the key element here is what is the size of the maximum stable set in the Johnson graph. So there's the bound by Graham and Sloan, which translates directly to our lower bound. And there's the upper bound that follows from the Hoffman bound. And honestly, I do not know which one should be the truth. So if you find anything that improves either bound, especially people in coding theory as well, would be very interesting. Because these stable sets relate to the maximum size of a binary code of constant weight. Yeah, if you improve the lower bound, then this immediately improves the lower bound that we have on sparse paving matrix. If you find anything to improve the upper bound, then this may be very useful to decrease the factor 2 that we have. So here's a nice plot that I took from my master's thesis, where I plotted, so the lower line with stars is the lower bound due to Graham and Sloan. The upper bound is basically the upper bound that we found. And there's some more upper bounds, which are the red boxes. I think they're taken from the paper by Graham's song. They have some upper bounds as well, which are very close to the Hoffman bound. And on the website of Andries Brouwer, I found a nice table, which are the brown dots, which are results of explicit constructions of stable sets. So also from this plot, it's not quite clear what we can hope for, right? There's other upper bounds that are close to the upper bound that we have. There's constructions that are close to the lower bound that we have, and I honestly have no idea which is the truth.
What about experimentation, randomly sampling independent sets?
No one knows how to do it.
Well, I mean, you can do a Markov chain on independent sets, right?
You'll get an independent set size about 1 over the degree fraction, which is probably bad. The degree
So
is
if you-
about n squared,
if you-
and these table sets are, the degree is, yeah, so if it's 1 over n squared fraction, these guys are 1 over n fraction. So that's the thing, they're very unlike
Yeah.
random sets. You can't just toss them together.
Yeah, so
They have
this is really
structure.
about maximum stable sets, not about typical stable sets.
And there aren't enough, you're saying there aren't enough of them to hope to discover them through random experimentation.
The structure of stable sets in the Johnson graph is not like sparse paving. Like, you know,
Exactly. Well, we don't really know, I think. Do we have any idea about the structure? So it would help to know something about the structure. And most sets of this size, stable sets, is just a couple of large stable sets, of which you could then have a table with subsets. I do not know which is the truth.
What's particularly impressive about that conjecture about sparse paving matroids is that it's not actually true for 8-element matroids.
Sure.
Not trying to. I remember saying that back then. Yeah.
Seven,
That's right.
7 element matrix.
Seven.
No, but the conjecture that was in Blackburn, Crapo and so on. You know,
Well,
paving matrix, sparse paving matroids predominate for n equals. Da, da, da.
It sort of depends on how you interpret predominate.
Yes, okay,
Yeah. It's not true that a majority are sparse paving
that's right. Or even paving.
or paving.
Right.
Yeah.
So,
But it's a serious fraction of all the measurements, right? Especially after your extension of that resulting measurement.
it's 49.5% on 8 elements.
Okay.
And then it goes up to 76%.
Yeah.
And then we think it goes up to, I don't know, 95% or something.
Yeah.
Yeah. So it makes it kind of likely that it could be true.
Yeah. No, I'm just interested. I mean, it's hard enough making a correct conjecture that fits with the established evidence, let alone making a correct conjecture. So,
Yeah, these are just some thoughts on how to improve. These are hard problems, so people in coding theory are very interested in this kind of problem. They've been working on it for 30, 40 years, and they still don't know how it works. Stable sets in Johnson. Okay, so there's another conjecture that I'd like to talk about, which states that almost all matroids have rank equal to n over 2 basically. This is maybe what you would expect in some weaker sense, perhaps, that there are many matroids that have rank close to this. The first result that I know of is due to Oxley Simple Washoe Welsh, who show that you can be off by some epsilon fraction of n.
at the heart.
Sorry?
Yeah, okay.
So this kind of tightens the bounds, right? It shows that most matroids have rank close to n over 2, but not quite equal to n over 2. And results that Rudy and I have together with Nikhil show that we can improve this epsilon n to something depending on root n. If the constant is larger. But this is just an application of the upper bounds combined with the lower bound of Graham's law of d that we have. But let's basically what it says over there. So yeah, it would be very nice to improve this in this further, right? So, particularly if we can improve this this log square to something that is much smaller, it would immediately translate to better balance on the rank of almost all matrices. There's a bunch of related conjectures to this. Almost all matroids have rank equal to n over 2, and they are somewhat weaker, I think. So maybe easier to find. Was that a bell for
That's lunch. Yeah.
Okay, so I'll go over it fast. So there's unimodality conjectures on the number of matroids. Either it's unimodal or log concave. Same for sparse paving matroids, and I don't think any of these have been proved up to now. So these are still open questions that would be very interesting. Maybe could lead to something to prove the conjecture. Okay, what's this? Matroids without circuit hyperplanes. So we've been looking at sparse paving matroids, and one of the equivalent definitions of a sparse paving matroid is that every R set is either a basis or a circuit hyperplane. So this leads to the following result. If we can show that almost all matroids are sparse paving, then almost all matroids must have a circuit hyperplane. This is because the only sparse paving matroids without a circuit hyperplane are uniform matroids, of which there are not many. So that may be easier to prove in some way. If you have a bunch of circuit hyperplanes, then you can relax them all and give them in a list. And the matroid that you are left with does not have circuit hyperplanes. So the bunch of circuit hyperplanes that you selected, it's just a stable set in the Johnson graph. And there's a matroid without circuit hyperplanes as well. So it shows that the number of matroids is at most the number of sparse paving matroids multiplied by the number of circuit hyperplane free matroids. So all these quantities are related to each other. Okay, and here's, I think this is...
that was already lunch plus 10.
Yeah.
We've got to keep the
Sure.
relations with the cook.
Yeah, this would be my final slide. So.